Welcome to Shanti-Peace for Mathematics. In this video, we are going to discuss about the D'Humble's ratio test. It is also known as a ratio test, which tells you that if you have a summation of an, which is a positive term series, and in that this limit of an plus 1 upon an is equal to L, then the following statements should be pulled. It says that if the value of L, which is the limit of this one, if it is between 0 and 1, then we can say that the series is convergent. And if the value of L, which is greater than 1, that means bigger than 1, then the series summation of an is divergent. And if L equal to 1, then we can say that the test is failed. That means you cannot predict that whether the given series is convergent or divergent. So here we are going to prove this theorem, and as well as we will discuss some of the examples based on this ratio test. So let us discuss the proof of this theorem. Here given that a limit of an plus 1 upon an is L as n tends to infinity. Definition of a limit, what we can say is for any given epsilon greater than 0, there exists n0 belongs to n such that mod of an plus 1 upon an minus L is less than epsilon for every n greater than or equal to n0. If I expand this modulus, then we can write down this is as minus epsilon less than an plus 1 upon an minus L is less than an for every n greater than or equal to n0. This I can rewrite as L minus epsilon less than an plus 1 upon an is less than L plus epsilon for every n greater than or equal to n0. So this statement is true for any given epsilon. So we can take the case number 1 here, that is if the value of L is between 0 and 1. Since L is a real number which is between 0 and 1, we can choose epsilon in such a way that L is less than L plus epsilon less than 1. That means in between L and 1, another number L plus epsilon which lies in between L and 1. And that is the property of real number that we have. Now, we'll use the inequality, this one, to prove our statement, that is summation of an is convergent by comparison test. So just observe that using inequality 1, we have, that is the inequality I am talking about, this is the inequality 1, we'll have an plus 1 upon an is less than L plus epsilon for every n greater than or equal to n0. I will call it this value as alpha. So here let us say alpha is equal to L plus epsilon. Now for any n greater than or equal to n0. So hence for any n greater than or equal to n0, we can write down this is as an upon an0. Now here I am multiplying and dividing some terms, that is an0 plus 1 upon an0. So since I have multiplied this one, I should divide that also. So an0 plus 1, numerator I am multiplying an0 plus 2. So if I multiply that one, I need to divide that an0 plus 2 and I should multiply with an0 plus 3 and so on. The last term was you have an upon an minus 1. So up to an0 to an minus 1 I am multiplying and dividing these terms. So only the terms left is an upon an0. Now this quantity, due to this equation number 2, this quantity is less than alpha because an plus 1 upon an is less than alpha for every n which are greater than or equal to n0. So it is true for n0, n0 plus 1 and so on. So that's why this will be less than alpha. This quantity is also less than alpha. This quantity is also less than alpha, and so on. This last quantity is also less than alpha. And there are alpha are there, but this n minus n0 times this alpha will be appear, because there are n minus n0 terms are there. So from this, what we can say is an upon an0 is less than alpha raised to n minus n0 for every n greater than or equal to n0. So therefore, this will gives you an is less than alpha raised to n minus n0 into an0 for every n greater than or equal to n0. This also I can write down an is less than an0 upon alpha power n0 into alpha raised to n for every n greater than or equal to n0. Let us recall what was the comparison test. In the comparison test, we say that if summation of an is less than or equal to summation of bn, and if the summation of bn is convergent, then summation of an is convergent. That means if the bigger series is convergent, then its smaller one is also convergent. So here is also we have the same situation, that this is a summation of an, and here on this side it is summation of alpha raised to n, and the summation of alpha raised to n is a convergence series. Due to this is a fixed number, because n0 is fixed, so this an0 upon alpha raised to n0 is a fixed number. So summation of alpha raised to n is a geometric term series, and with the alpha value of alpha is, as per the equation number 2, the value of alpha it is less than 1. So that's why this summation of an is convergent. So let us write down that since n0 is a fixed integer, an0 upon alpha raised to n0 is a fixed finite number. Let us say that number is k. Say it is k. So thus what we have is, for every n greater than or equal to n0, we have is an is less than k times alpha raised to n. But summation of alpha raised to n is a geometric term series with ratio alpha which is less than 1. Therefore, by comparison test, the summation of an is convergent. So here we have did the proof for the case number 1. That is, if the value of alpha, if the value of L is less than 1, then we can say that the summation of an is convergent. Let us try to do the case number 2. The case 2 is says that L is greater than 1. So we need to select, let us select a positive number epsilon such that L minus epsilon is greater than 1. Let us consider this L minus epsilon is equal to beta, which is the greater than 1. And since we have given that limit of an upon bn is equal to 1 due to because of equation number 1, so using inequality 1, now instead of using inequality in that 1, we have used previously this inequality, now we'll use this one. So from that what we can say, it is an plus 1 upon an is greater than L minus epsilon, which is equal to beta, for every n greater than or equal to n0, but instead of n0 maybe it is some different terms will be there. So let me take it is n1. Now for any n which is greater than or equal to n1, we start with an upon an1. As we have did in the previous case, we will multiply and divide some terms here. So that terms is an1 plus 1 upon an1. Since I have multiplied this one, I need to divide that. That is an plus 1, an plus 2 I multiply and divide that same term. Here multiplying with an plus 3 and so on. The lastly we have it is an upon an minus 1, and this quantity, the first quantity, is greater than beta due to this equation number 3, or I can say inequality 3. So we have this beta into beta up to beta. There are n minus n1 times beta will appear. So that's why this is equal to beta raised to n minus n1. So therefore we get an upon an1 is greater than beta raised to n minus n1 for every n greater than or equal to n1. Now from this what we can write is finally it is therefore an is greater than an1 upon beta raised to n1 into beta raised to n for every n greater than or equal to n1. Due to this, if you multiply both sides by an1, and an1 is a positive, so no problem with the inequality will not be changed. And since this n1 is a fixed positive integer, an1 upon beta power n1 is a fixed finite number. Let us say that number is k1. Thus, for n greater than or equal to n1, we have is an is greater than k into beta power n for every n greater than or equal to n1. But this summation of beta power n is a divergent series due to it is a geometric series with common ratio beta, and beta is greater than 1 here, as we can see that the value of beta is greater than 1. So that's why this summation of beta power n is divergent, and by comparison test we can say that the summation of an is also divergent. But summation of beta power n is a geometric series with ratio beta which is greater than 1. Therefore, summation of beta raised to n is divergent, and therefore by comparison test summation of an is divergent. Now the case number 3, it is left to prove that if L is equal to 1, then the test fail. So that means we need to produce a two series in which the limit of an upon an plus 1 upon an is 1, but one series is divergent series, another one is a convergent series. So let us produce that two example. So consider the series summation of 1 upon n. So here the sub case A that we can consider. Here we have an is 1 upon n, and let me calculate what is summation limit of an plus 1 upon an as n tends to infinity. So that is limit of an plus 1, that is 1 upon an plus 1 upon n as n tends to infinity. So that's why this is limit of n tends to infinity n upon an plus 1. And you know that if I divide by n both sides in the numerator and the denominator, so we'll have 1 upon 1 plus 1 by n, that will gives me 1. So this is the value of L, which is 1, but by P series test summation of 1 upon n is divergent as the value of P is 1, and we know that, let us recall what is a P series test. Summation of n power P is convergent if P is greater than 1, and divergent if the value of P is less than or equal to 1. So here the value of P is equal to 1. So that's why this summation of 1 upon n is divergent. So this is sub case A. It says that summation, this limit of an upon an plus 1 upon an is 1, but the summation of 1 upon n is divergent. Let me produce another example, that is the sub case B. Consider the series summation of 1 upon n square. Here an is equal to 1 upon n square. Let me calculate what is summation of an plus 1 upon an as n tends to infinity. So that is limit of n plus 1, so that will be 1 upon n plus 1 square upon 1 upon n square as n tends to infinity. So that can be simplify as n square upon n plus 1 whole square as n tends to infinity. That we can write down limit n tends to infinity. If I divide by n square in the numerator and the denominator, will have 1 upon 1 plus 1 by n whole square, and that will be 1 due to 1 upon n tends to 0. But this summation of 1 upon n square is convergent due to the p series phase. Here the value of p is equal to 2. But the series summation of 1 upon n square is convergent by p series test, because you know that the value of p is 2, which is greater than 1. So here in the sub case 1, we have produced one example in that summation of an plus 1 upon an is 1, which is divergent, and in this example summation of an plus 1 upon an as limit n tends to infinity is 1, but in this example it is convergent. So what we can say from, so therefore by sub cases a and b, we say that if L is equal to 1, then the test failed. Let me give some examples here. 2 examples will do and will complete this video. So the question is, test the convergence of n factorial upon n power n running from 1 to infinity. Here you just observe that what is your an? An is n factorial upon n power n. So what will be the an plus 1? Which will be n plus 1 factorial upon n plus 1 power n plus 1. Now let me calculate what is limit of an plus 1 upon an as n tends to infinity. So that is limit of n tends to infinity. An plus 1, that is this value, will substitute here, that is n plus 1 factorial upon n plus 1 power n plus 1 into an, that is n factorial, and in the denominator you have n power n, but that goes into the numerator, so that's why it is n power n here. This I can simplify as n tends to infinity. This n factorial will cancel out with this n plus 1 factorial and left with n plus 1. The 1 n plus 1 is cancelled with this one. So the quantity it is left, it is n upon n plus 1 power n. This I can write down as 1 upon 1 plus 1 by n power n. So I'll divide here in the inside this bracket numerator and the denominator by n, will left with this one. And this is very well known series, it is of E, so that's why it is 1 upon E is the answer. So this here I have used this limit 1 plus 1 upon n power n as n tends to infinity is equal to E. This limit is very well known limit, I am using that one here, and the 1 upon E is less than 1, that we know. So therefore what we can say, that therefore the given series, that is summation of n factorial upon n power n, is convergent by ratio test. Let's solve another example. This is the convergence of summation of n power n upon n factorial. Here just I take the reciprocal of this one. Consider an is equal to n power n upon n factorial. So here n plus 1, you will have n plus 1 power n plus 1 upon n plus 1 factorial. Let us calculate what is the limit of an plus 1 upon an as n tends to infinity. So that's why limit of an plus 1 upon an, that is this, we can substitute, that is an plus 1 power n plus 1 upon n plus 1 factorial. In multiplication, you will have this term, that is in the denominator you have n power n, and the denominator you have n factorial, that goes in the numerator, so that's why it is n factorial as n tends to infinity. You just observe that this n factorial will cancel with this one, left with n plus 1, and 1 n plus 1 is cancelled with here, and it will left the quantity here, it is limit of n plus 1 upon an raised to n as n tends to infinity, that I can rewrite as 1 plus 1 by n raised to n. This is the value of e, which I already told you, that is greater than 1. So therefore, by ratio test, summation of n power n upon n factorial is diverged. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or a question, please drop down in the comment box below. See you in next video. Till then, bye bye. Sayonara.